We have now Dr. Panagiotis Gonidakis is going to present about segmentation and feature engineering of coronal structure using SDO, AIA, and HMI data. So we are still keeping in the same area. And it's my pleasure to introduce Dr. Panagiotis Gonidakis, who is a postdoc researcher at K11. Panagiotis is a data scientist, and now is specializing in deep learning, and is working now as a project applying AI machine learning to space science and exploration mission. And he holds a PhD from the Bree University Brussels. So very lucky to have you today. Looking forward for your presentation.
Thank you very much. Thank you for the invitation and a nice presentation. So today I'm going to talk about segmentation, feature engineering of solar coronal structure using SDO, AIA, and HMI data. The outline of presentation is after a brief introduction. I'm going to describe how we can do the segmentation using two ways, one based on deep learning and a unit open source framework. Then performing the same operation, but in a different way, using classical computer vision operations. And then as soon as we have the segmentations, we want to characterize the segmentations with some feature, handcrafted feature selection, and then we can represent the segmentations, and then we can do some clustering, and we can discuss our result and present some future work. So if we observe some AIA data and we can see our sun, we can see some very interesting areas that we want to detect. First of all, we have the active regions, like the one that the yellow arrow indicates, where this is the main source of flares and CMEs. That it's very important here on Earth to early detect and identify these kind of events to protect technology infrastructure here on Earth. Then we have some dark areas that they're called coronal holes, like the area indicated by the red arrow, and these areas play a significant role in studying the solar wind. And then we have other structures like coronal bright points and filaments. But in other contexts, one can detect them. But in the context of this project, we want to separate from coronal holes and active regions. Concerning the data, as we have said before, we're using Solar Dynamics Observatory data from SDO, and specifically we have the level 1.5, let's say, data set, which from Galvez and collaborators, and they include data from 2010 and 2020, and then we pre-process a bit more in order to reach level 2. Since we want to perform segmentation, which is going to be data-driven in a supervised way, we need also some annotations, not only the data, but the masks describing the segmentation that the AI model needs to produce. So we use some custom masks and some software to have these masks. And an example is this POCA. It's a set of algorithms that have been introduced in the past by the Observatory of Brussels. In order to evaluate these segmentations, we use either die-score, either IOU, intersection of a union, intersection of the union, sorry. So the first algorithm that I'm going to present is a unit-based. These networks have been introduced in biomedical image segmentation field, but have been applied in a wide range of fields. So it consists of convolution blocks. Then we go to a small representation of the data, and then we deconvolve again to have our output mask, which its resolution is the same as the input. Our input is a 256 by 256 grayscale image. And after the blocks of convolutions, we have a small representation of the data, 16 by 16, and then we go up. And in order to recover some precious data that might have been lost, we have skip connections. Each convolution block consists of 2 pairs of 2D convolutions, 3 by 3, ReLU activations, and batch normalization. And there's also dropout. So this is a pretty heavy framework, but it works well. So prior to training, we do intense data augmentation. Some rotations and some transformations are not physically possible, but it helps the model to get more data and to have better representation of the data and to have better performance. So using the same model, we can produce 2 set of weights. One set of weights is done to recognize active regions, and another model with the same architecture but different weights in order to identify coronal holes. And this UNet consists of 78 million trainable parameters. First is I'm going to present the active region segmentation model. It has been trained on data from 2013 to 2015. We get one image per day, and then we have an individual test set with 360 images. So using the pre-mentioned scores, we can acquire dice score of 0.62, and if we get the masks and do some thresholding, we can improve a bit both metrics. So there we can see some results when we have the ground truth mask, the prediction, which is the output of the UNet, and then we will overlay the mask to the image. We can have these nice figures. So here, if we want to have some more insight of our results, here's the distribution of the dice score in the test set. So actually, we can achieve in the almost the majority of the images dice score above 0.6. And if we compare the SPOCA masks with our network, we kind of underestimate the annotated area, and it remains to further investigate it if this is important or not. For the second model, where we want to identify coronal holes, we use 193 Armstrong data, and we use other software to produce massive amount of data, and then we train more or less the same amount of images with there is a 1 year extra, and then we have again an independent test, and with the same metrics, we can acquire a bit higher performance, so 0.8 dice, and if we again threshold a bit this mask, we can actually improve our results. And here again, in the same way, we can represent the mask, the ground truth mask, our prediction, and overlay them to the original image. And again, if we want to see the distribution of the dice in our test set, the majority of almost all of the images can score above 0.8 dice score. And here, the softwares that have produced the masks have similar performance with the UNet. So if we want to do something a bit different in order to find an alternative, in order not to have a so huge model and very heavy, we can actually get inspiration from some methods that have been here before the deep learning era, and we can use some classical computer vision algorithms. So first, we can do some basic automatic thresholding, and we can extract high intensity and low intensity areas. The high intensity will represent mostly active regions, and the low intensity will represent coronal holes. And as soon as we have these masks, we can actually compare our algorithm to our UNet. And if we go a bit further, for these two algorithms, we can actually get a set of segmentation areas. And for each area, we can extract a set of figures. And then we can represent these areas in a multi-space feature space. And doing some image, some dimension reduction using PCA, we can go to a lower dimension space, and then with some clustering, we can actually, in unsupervised way, characterize these areas. Because remember, our goal is to identify areas that could actually lead to this physical phenomena like CMEs or flares. So if we go a bit deeper to this framework, basic automatic thresholding methods inspired for computer vision have been tested. The most accessible was O2. The simple version of O2 was developed to identify from general computer vision images, to identify the foreground and background. In our case, using multiple O2, so have various automatically calculated thresholds, we can actually easily extract coronal holes and active regions. And if we evaluate in a small test right now, we have which consists of about 10 and 20 samples, we can achieve rates between 0.5 to 0.6, which is close to the UNet, but still we need to further evaluate that and automate, because the test at this moment is really not really nice representative. So then we can extract a set of features that have been selected based on some literature review. And then by plotting the correlation matrix, actually we can do some feature selection, and we can have a bit smaller list of features. And then we can actually do some clustering. So first of all, we can differentiate with a high value threshold using TSNE, which is a nice algorithm to do some clustering. And here we can first identify the optimal number of clusters, which with the needle method, we see that it's not, we need to have 4 clusters. So they're nicely separated, and then by just manually observing what has been clustered, we can see that more or less based on the area, we can actually differentiate bright points and active regions. And so that's good results, but we would like actually also to have some separation between limb brighting, but it's an ongoing work and discuss potential to get some more improvement. And if we go to low value threshold, then actually we want to identify coronal holes. Again, with the needle method, we found that we can have 5 clusters, and again, more or less based on the features describing the amount of area, we can cluster small coronal holes and big coronal holes, some dark points. And here we can actually see how these clusters can form the feature space. The same work has been done also for HMI data, but this was more complicated to fine-tune it. So again, it works to have some clusters, and it remains to interpret better the results and play with the parameters to see if this can also can assist us. So now I would like to step behind and say why we need this kind of segmentation, what would actually help us. And here it's one example use case. We have solar orbiter, which has 2 telescopes, one that represents the full disk of the sun, and then we have also a focused, which actually we can have high resolution images, but from a much smaller field of view, which can vary from 6 times or even 31 times different than the first telescope. And we need then to have a strategy and have a selection where this telescope would actually focus and to acquire meaningful and useful scientific images. So this kind of segmentation would actually give us a proposition where we should focus and how we should carefully design the mission in the coming months in order to acquire the desired data. So this kind of algorithm can also be, this kind of example can also be designed for our project and can be linked with other Orchid package tool algorithms that we designed this project. So in my presentation, I described 2 ways how we can segment active feature coronal holes mostly. Then we can actually extract some features and do some clustering. And future work actually includes ways to simplify first the UNet, because as you saw, we have 5 pairs of convolutions. We'll try very soon to reduce the amount of convolutions and see what's the impact on performance, and also find way to see if I remove the skip connections would be the information that we get to this very small representation, 16 by 16, would be sufficient in order to reproduce accurately nice masks. And regarding the more traditional framework, it would be further automated in order to easily evaluate the same amount of images in order to compare with a UNet, and then ideally find the best compromise, which framework would be more applicable to further develop and optimize to be hopefully deployed in some years to come in a future mission. Thank you very much for your attention.
Thank you very much, Panagiotis. Question, comments?
Hi, everyone.
Daniel?
As I understand, the 2 algorithms, they perform the same clustering and feature and so on. But the machine learning one is very hardware intensive. So can you explain again why would I choose that instead of the classical computer, which is lightweight and they could even maybe put it on board of the face prep, for example?
Yeah, so this is the UNet. On the ground, if we would like to have it on ground, it would be perfect. It's very accurate, but as you really nice say, that it's really hard to deploy it in a feature spacecraft. So that's why our effort is to find its limits and find a compromise, how we can actually strip anything that this can be heavy, and see what's the input, what's the output, what's the impact on the performance, and then evaluate what are our needs. And if we manage to have a light version of this, then it would have the potential to be deployed.
Okay, so if I'm processing on Earth, I will choose that one. If I'm processing spacecraft, I would use the computer vision one, something like that.
It's not so simple, because actually we could have, our goal is to have a light version of this. And then we could actually try to deploy this on a spacecraft. And we will have collaboration with our KTH collaborators towards this. We'll get some tips what is very heavy, what would be great to remove. Because also this one, you have to imagine that it does some thresholding, has this multiple O2, also TSNE and K-means, or this kind of algorithms. They run nicely if you have a CPU here on Earth, but still, it's not sure that it will be easily deployed in a spacecraft. And also, these kind of algorithms are not. It's very, let's say, we don't paralyze it, so you cannot benefit from a GPU. Which our goal is to have a FPGA with. And I'm not a hardware person, but our focus is to parallelize all this using a GPU. So probably we need to have also powerful CPU. You have to make a choice probably. And again, I'm not an expert, so that's why we're collaborating with people from different disciplines. So we are designing our algorithms, and we get some feedback how we need to change them in order to go to the next level of deployment.
Savas?
Yeah, my question was a bit more practical, like the knee method to find the clusters. At least in some cases, it almost looked like it was a continuum. Like indeed, you can find the optimal one. Is that because the features or the images you're using are not necessarily producing clear clusters, or is it just a physical problem that does not have particular? Like in this one, my eyes would say those are 3 clusters.
Yeah. So the way that they are. The feature in the reduced feature space, they are projected. You can either have 4 We're gonna have, I have 2, we're gonna have 3. We have some other figures, but now in 15 minutes we will present everything. So it is a choice. You have the recommendation from the needle method, but then you can actually, if you want to have only 2, you can have it. It's just a choice. But the algorithm says that I can provide you, based on the data you have, I can provide a good separation using 4. Don't go, let's say 8. I wouldn't be able to separate nicely.
Are there other methods? That's on the silhouette method, though, right? So are there other methods that can be used to determine the optimal, or all of them are consistently the same?
We used in this project only needle. Indeed, there are some others, but we didn't run it for this context. But probably we'll have similar results.
Thank you. Other question, comments? Now let's thank Panagiotis.